Welcome to Digital Electronics 33301 FlipFlop and Latches. This is the third part of the lecture. So let's start with the JK FlipFlop. Let me use the laser pointer. Okay. So for JK FlipFlop, Q and Q prime are feedback to the pulse steering AND gate. There is a no invalid state for JK FlipFlop, and also there is a toggle state. So when your J is high, this is called set state. Obviously your K is low. When your K is high, obviously your J is low, this is a reset state. If both input low, then no change. If both input high, then toggle. So previously for both input high, that was invalid state. Right now we can rectify the circuit so that it becomes now toggle. So this is a typical representation of K flip-flop. You have J and K as an input. This is your latches, NAND latches. This is your pulse transition detector, which is detecting the pulse whether it is positive edge or negative edge. And this is your characteristics tables. So at the clock edge, if your JK is 0 0, so no change. 0 1, so 1 means K1 means reset. J1 means set, so set and reset is 0, and 1 on toggle. Previously it was invalid. So if you look at here, so this is Q is your present state, Qt plus 1 is your next state, and J and K is your inputs. So for first four situations, if your present state is 0, so what will happen in the next state? So if your JK is 0 0, for 0 0 no change. So previously it was 0, so it will be 0 next state. For 0 1, for 0 1 it is reset. So it's resetting to 0. Previously it was 0, again it's resetting to 0. 1 0. So for 1 0 it is set. So whatever value you have in Q here does not matter, it will be set to 1. For 1 1 it is toggle. So previous value was 0, and now next value will be 1. Look at here, 0 0. Again for 0 0, this is for last this 4 state where our present state Q value is 1. So for 0 0 no change. No change means previous value is 1, so it will be 1. For 0 1, so 0 1 means reset, so it will be reset to 0. Previously it was 1 but reset to 0. 1 0 1 0 means set, so set to 1. 1 1 means toggle, so previously it was 1, it becomes 0 now. So if you do the K-map and simplify it for Qt plus 1, you'll find this kind of equations. So if you put all the values in the K-map, so Q of t plus 1 equals j dot q prime plus k prime q. So now let's discuss about the T flip-flop. So T flip-flop is a single input version of JK flip-flop formed by tying both inputs together. So what does it says, like that was similar to his JK, so that was your J, that was your K, but if you try this K with this one, it becomes T flip-flops, so this becomes shorted here. So here right now we have one input instead of two for JK. So for T flip-flop we just have one input, so this K becomes shorted with J, and that becomes T flip-flop. This is your clock, and this is your Q and Q prime. So for T flip-flop, the characteristics table will be like this. When there is a clock edge, it could be positive and negative. If T is 0, that means no change. If 1, then toggle. So when 0, no change, 1 toggle. So just look at here. Q is your present state values, Qt prime T plus 1 is your next state values, and for T is 0, the output will be 0. When T is 1, 1 means toggle, so the previous value was 0, so it becomes 1. For last two, when your Q is 1 1, for T 0, so 0 means no change. So previously you have 1, so it will remain as 1. Then t equals 1, so when t 1, 1 means toggle. So previously you have 1, so toggle means 0, so it becomes 0. Again, if you simplify this and draw the KMF, and you can find the characteristics equation, something like this: q of t plus 1 equals t q prime plus t prime q. So for t flip-flop, so it has lots of applications. So one of the common application is frequency division, which will be mostly covered in the counter lecture. So if you look at here, this is your basically T flip-flop, because your K is shorted with J, and you have the clock as well. This is obviously rising edge of clock. If you look at here, so this is your clock. So whenever your T is 0, it will remain as it is. Whenever 1, so it will be toggling. If previous 0, 1, if 1, then 0. So it says it's connected to high. So what will happen here with Q? So it will toggle, right? So if initially it's 0, so at the clock edge it becomes 1. Then next clock edge it becomes 0. So remember that here it is changing its state only at positive edge, because this is positive edge. But one important thing is, for the clock, if you look at the period, so period is up to this one, right? But here your periods becomes almost double, right? And your frequency is getting half. So it is called divide clock frequency by 2. Just if you look at here, so this is again two uh, T flip-flop cascaded together, but important thing is here your output. So this T flip-flop output is working as a clock for this one. So that's why your clock frequency got divided by 4. Just if you look at here, so this is your clock, and QA is output of this one. So it becomes divided by 2 clock frequency, and after this one it becomes divided by 4. Just if you look at here, so the period becomes double here, or double up to for QA to QB is double again. That means 4 times. Or in terms of frequency, so it's getting half or 1/4, or which is also called divide frequency, clock frequency by 4. Anyway, so we'll use this kind of arrangement in the counter lecture. Okay, so now this part is very important. So we'll discuss about the truth table, the characteristics table, and excitation table. So truth table we already know from the flip-flop or latches. Say like for SR flip-flop, we know at clock edge, so if our input is 0 0, it will be no change, or memory 0 1. The next state will be 0 1 0, next state will be 1 1 1, it will be invalid for SR flip-flop. So this truth table will be helpful to get the characteristics tables. So what characteristics tables tell such? So instead of SR, we also have another input as QN. Obviously, all of this happen at clock edge. That's why clock equals 1. We need to determine the next state, Q of n plus 1. So this is your present state, you can say, and this is your next state. So how we can determine the next state? So say like we have right now 8 uh, combination. Like for SR, this is basically 0 0 0 1 1 0 1 1. But as you have 3 input, for this 3 input you have 8 combinations, so you can write 0 to 7. Okay, so if you look at here, whenever your S is 0, R is 0, for 0 0 0 0 no change. So previously you have 0, so it will be 0 0 1. So 0 1 says 0, so it will be 0 to reset. And 1 0 is set, so 1 0 set 1, so it will be 1. again 1 on, so 1 on is invalid, so that means don't care. Again 0 0, so 0 0 no change, so you have previous value 1, so it will remain no change 1. 0 1, so 0 1 is reset to 0, so reset to 0, it doesn't matter what was previous value was, so next value will be 0. 1 0, again 1 0 will be set, so it will be set to 1. 1 1 will be don't care. Okay, so this will be helpful to determine the excitation table. So if you look at the excitation table, so right now we also have Qn. This is your present state, this is your next state, and this is your S and SR. So for this we have combination 0 0 0 1 1 0 1 1 1. We need to determine the S and R values. Okay, so if you look at here, so Qn and Qn plus 1, Qn is here, Qn plus 1 is here. So 0 0 state we have, like for these two Qn is 0 0, for these two this and is 0 0. So we will consider then these two values. Okay, so these two rows, basically first two rows. So for Qn 0 and Qn plus 1 0, our S is 0 always, but our R is changing 0 to 1, so we can write S equals 0 and R equals don't care, that means it can be 0 or 1. Next one 0 1, so when Qn 0, Qn plus 1 1, our S become 1s, R become 0, so 1 0. When 1 0 1 0 means this one, so you can check the color as well, so 1 0. So S becomes 0, R becomes 1, 0 and 1. Now for 1 1, so 1 1 means this one 1 1, so this is one of the state and another is 1 1, this is another one, right? So here if you look at here, your S is changing 0 to 1, R is fixed, so R we can write 0, for S as it is changing 0 to 1 we can write cross. So this is your excitation table. So after determining the excitation table, so we can use it for different applications. So now if you want to calculate Q of n plus 1, what you can do, you write Qn here, this Qn, S and R here. So if you draw the K map, so this is 0 to 7, so put the values of these values 0 to 7 and do the grouping. So this is our first group, this is second group. So if you calculate this, simplify this, you will find Q of n plus 1 equals S plus Qn into R prime. SRD and JK inputs are synchronous inputs. As the data on these inputs are transferred to the flip-flop output only on the trigger edge of the clock. For asynchronous input, it affects the state of the flip-flop, which is independent of clock, right? Preset or clear, also direct set and direct reset. When preset is high, Q is set to high. When clear is high, Q is immediately clear to low. For normal operation, the flip-flop operate like when preset is and clear are low, so our flip-flop operate in normal condition. With preset and clear low, this is active low, preset and clear. So when our preset is low, then output will follow the preset. When our clear is low, like clear low, this portion output will follow the clear, and within this region it will do the normal operation. As it says J and K and high, that means it will act as a toggle flip-flop. So this toggling the values, we will discuss this in the counter lecture. So here are a couple of assignment for you. So this is master slave flip-flop, which is very important concept, and race around condition, which will be needed to understand the master slave flip-flop, and also difference between latches and flip-flop. I suggest you try to follow the textbook. Also, you can try the NESCO Academy and NAS lecture series of digital logic. Thank you.